Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I am going to discuss the concept of numerical integration. In the previous lecture, I discussed the analytical methods of performing integration. So, numerical integration is a little complicated concept, and numerical integration is required whenever we have complex functions or complicated functions whose integration cannot be evaluated by simple analytical methods. So, at those places, numerical integration techniques have to be adopted. So, in numerical integration, the first thing is the Riemann sum. So Riemann sum can be defined as S equal to summation I is equal to 1 to n f of xi steric into delta xi, and here delta xi is equal to x minus xi minus 1, and this xi steric belongs to xi minus 1 up to xi. So this xi steric varies from xi minus 1 up to xi, and if we assume that this xi steric is equal to xi minus 1, that will be called as left Riemann sum. If we assume that this xi steric is equal to xi, then that will be called as right Riemann sum. And if this xi steric is equal to the mean value of xi minus 1 and xi, then that will be called as middle Riemann sum. And this middle Riemann sum is also called trapezoidal rule, which we will discuss later. So suppose we have such a function which varies from 0 to 4, and first we have to define delta x, and delta x is called as the step size. So this whole continuous function is actually divided into discrete parts, just as we do in sampling of a function. So we have made four samples in this problem, and this is the first sample, this is the second sample, this is the third sample, and this is the fourth sample. And the width of each sample is equal to delta x, and mathematically this delta x is equal to b minus a over n. A is the lower limit of the function, b is the upper limit of the function, which is 4, and n is actually equal to the total number of samples. In this case, we have assumed that total number of samples are equal to 4, so the width of each sample will be equal to 1 in this case. So we have to do the summation in evaluating the Riemann sum of each sample, right? And then we have to multiply all the summations with delta x, which is the step size. Okay, so this is delta x, and we have to do the summation for all the samples within this function, right? So this is our first sample. If we assume that for one sample, the value of the function is constant and is equal to the left value of the function at the sample, then that will be called as the left Riemann sum, which we have assumed in this case. So for this sample, the value of the function at left hand side of the sample will be considered. So for the first sample, the left hand side is equal to this value. The left hand side of the function value is equal to 0. So 0 value, constant value of 0 is assumed for this sample. For the second sample, this is the second sample from point 1 to 2, and at the left hand side of the sample, this is the value of the function. So that value will be considered as constant throughout this second sample. For the third sample, the left hand side of the sample is equal to this value of the function. So for the third sample, this value will be assumed as constant throughout the sample, and for the fourth sample, this is the value of the function at the left edge of the sample. So this constant value will be considered for the fourth sample. So for each sample, we have assumed the value of the function at the left hand side of the sample. So that is called as left Riemann sum. So now we will add all these values of the function, these constant values, to get the left Riemann sum. So in the right Riemann sum, we will be assuming the value of the function at right hand side of the edge of each sample. So we will also see that when we discuss the right Riemann sum. So for the left Riemann sum, S is equal to delta x, right? So this is the expression for the Riemann sum. So this is delta x, and this is the value of the function for the first sample, right? So this is f of a, right? So this is a plus delta x, this is a plus 2 delta x, this is b, and this is f b minus delta x. So s will be equal to delta x multiplied by f of a plus f of a plus delta x plus f of a plus 2 delta x plus so on, and the last value will be f of b minus delta x. So for the last sample, the value of the function is actually the value at this instant equal to 3 or b minus delta x. So this is the last value of the function for the last sample, and the sum will be equal to delta x times this summation. So this is called left Riemann sum, and as I have told, the right Riemann sum will be evaluated as follows. So this is the first sample, and for the first sample we will assume the value of the function at the right edge of this first sample. So this is the first value, this is the second value because this is the value at the right edge of the second sample, and this is the third value, which is the right value, the value of the function at the right edge of this third sample, and this is the fourth sample, and again we have considered the value at the right edge of this fourth sample. So in this case, this is our first value, and this is equal to f of a plus delta x, this is f of a plus 2 delta x, and the final value will be equal to f of b, right? So s is equal to delta x multiplied by f of a plus delta x plus f of a plus 2 delta x plus so on, and the final value will be equal to f of b. So clearly the difference between the left Riemann sum and right Riemann sum can be observed from here. So now let's discuss the midpoint Riemann sum. And in the midpoint Riemann sum, the value of the function at the midpoint of the sample will be considered. So this is the first sample, and at the midpoint of the sample, this is the value of the function. So that value will be considered as constant for the whole sample. This is the second sample, and the value of the function at the midpoint of the sample will be considered as constant for the second sample. This is the third sample, and this is the fourth sample. And for all these samples, we have considered the value of the function at the midpoint of each sample. So mathematically, for the midpoint Riemann sum, s will be equal to delta x times f of a plus delta x, right? So this is f of a, this is f of a plus delta x. So midpoint value will be f of a plus delta x by 2. This is f of a plus 3 delta x by 2. This is f of a plus 5 delta x by 2. And this will be f of b minus delta x by 2. So this is f of b. This whole step size is delta x. So this will be f of b minus delta x by 2. So that was the midpoint Riemann sum. And midpoint Riemann sum is also called trapezoidal rule. So let's solve an example, and we will solve this example by using all the three methods of Riemann sum and compare our answer. So in this example, we have to evaluate the exact area of the region between the parabola y equal to x square and the x-axis on the interval from 0 to b, and use Riemann sums. So this interval from 0 to b is first divided into n parts, and delta x will be equal to b minus 0 divided by n. So this will be equal to b over n. And let's first evaluate the right Riemann sum, and height of the boxes will be x1 square, right? So this is the first value of the function. This is the second sample, x2 square, x3 square up to xn square. So here we can see that x1 is equal to b over n, right? X1 is equal to b over n, x2 is equal to 2b over n, x3 is equal to 3b over n, and in general xi will be equal to ib over n. So xi is equal to ib over n. So by mistake I have written 2 over here, in fact it is b. So xi is equal to bi over n, and the final value xn will be equal to b. So area of each box will be 2 divided by n multiplied by x I square, right? So s will be equal to, this is delta x, which is equal to b over n, and these are x1 square plus x2 square plus so on, this is xn square. and xn is equal to b, so this is actually b square, and it is written as n b over n square, and area of each box will be equal to b over n multiplied by xi square. So let's evaluate this sum. So b over n square can be taken as common, so it will be equal to b over n cube, and in this bracket we will have 1 square plus 2 square plus so on up to n square, and this summation of squares is generally equal to n into n plus 1 into 2n plus 1 over 6, right? So let's solve this. So b cube over n cube into this expression, and it will become b cube over n square, and n plus 1 into 2n plus 1 is equal to 2n square plus 3n plus 1 over 6. Now this is our right Riemann sum. Now if we assume that this n is equal to infinity, or if we assume that these number of samples are assumed as infinity, then the right Riemann sum will be equal to, so let's put the limit of n tends to infinity, so in that case s will be equal to b cube over 6, and n square can be divided by these three terms, so it will be equal to 2 plus 3 over n plus 1 over n square. So after putting this limit we will get b cube over 3. So in general, if we take the integral of x square, it is equal to x cube over 3, and if we put the limit of 0 to b, we will get the answer b cube over 3, and that is the same answer which we have obtained using right Riemann sum for infinite number of samples. So it means the Riemann sum is similar to the integration. Okay. So let's again solve this example using a left Riemann sum. So if we assume left Riemann sum, then our first term will be equal to 0, second term will be equal to b over n, and final term will be equal to n minus 1 b over n. So this summation will be equal to b over n cube 1 square plus 2 square up to n minus 1 square, and in general this summation can be written as n minus 1 into n into 2n plus 2n minus 1. So again the general form of this summation is the same as we have used over here, n into n plus 1 into 2n plus 1. Here the number of terms were equal to n, but in the case of left Riemann sum, the total number of terms are actually n minus 1. So we will put n minus 1 in place of n in this expression. So it will become n minus 1, this will become n, and it will become 2n minus 1. So this is 2n minus 1. So let's solve this expression and put the limits of n approaching infinity, and again in that case the final answer after putting the limit is b cube over 3, and this is the same answer as we have obtained for the right Riemann sum. Now let's solve this same problem using midpoint Riemann sum or the trapezoidal rule. So in that case again delta x will be equal to b over n, and in s will be equal to delta x, and this is the midpoint value. So 0 plus b over n divided by 2 square, this is the first term, and the second term will be b over n plus 2b over n divided by 2 square plus so on, and this is the last term. Okay. So uh, delta x is equal to b over n, and we have 1 by 2 square with each term, so it is equal to 1 by 4, which is taken as common, so delta x is equal to b over n, and here we will have b over n square plus 3b over n square plus 5b over n square plus so on up to 2n minus 1 into b over n square. So again b over n square can be taken as common, and we will have 1 square plus 3 square plus 5 square plus so on up to 2n minus 1 square in the brackets. So this sum of the squares of the odd terms is equal to n into 2n plus 1 into 2n minus 1 divided by 3, and here we have 1 by 4 b over n cube. So this can be simplified as 1 by 4 b cube over n square into 4n square minus 1 over 3, and it is equal to 1 by 12 into this expression. So now let's put the limit of n approaches to infinity, and after putting this limit the final answer will be evaluated as b cube over 3, and again this is the same answer which we have obtained for right and left Riemann sums. So that is all about our discussion on the Riemann sum, which is a numerical method of integration. And I hope you have understood the concept of Riemann sum. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.